Consider solving trigonometric equations algebraically. We can do all of these problems without a calculator. So if we want to solve when sine x is equal to root 3 over 2, what we can do is just remember that sine x is y over r. So root 3 is y, 2 is r. Sine x is positive in 2 quadrants. Using all students take calculus, I know that my answer is going to be in quadrant 1 or in quadrant 2. So I know that this is going to be my 1, 2, root 3 triangle, which has a 30-degree reference angle, or pi over 6 reference angle. So that's going to be up here where y is the long side of the triangle. So my y is a long side, here, here, and x is the short side. So x is 1, y is root 3, and r is 2. And in quadrant 2, y would be negative. Okay, so now I just need to find out my angle. This is 1, 2 30-degree angles. So 2 pi over 6, or 3, 4 pi over 6. Those are my two solutions for part A. To find the general solution, I know that this is going to repeat many times. If I draw this on a graph, then really the sine function looks like a wave, starting at the middle, going up, keeps going like that forever. It repeats. I want to know where is that equal to root 3 over 2, which is about 0.866. So I found the first two crossing points as being 2 pi over 6 and 4 pi over 6. And now I want to know the general solution, so how could I get all the crossing points in all directions? Well, in order to get from the first point to the next point, I just have to add one of the periods. So because this is just a basic sine graph, I know the period is 2 pi. It takes 2 pi to repeat. So I'm going to take my answer and add 2 pi n times. Or I could take my second answer and add 2 pi n times, where n is an integer. And that would be called my general solution. Now, the second example, find the value of cosecant x if tan is 1 over root 3, and I'm looking from pi to 3 pi over 2. So let me label my graph here. I've got 0 to pi over 2. Pi is the same as 180 degrees, and 3 pi over 2 is 270. So looking from pi to 3 pi over 2 means that I'm only considering the angles in quadrant 3. Now the problem tells me that tan x is 1 over root 3, which is the same as y over x. So now because I'm in quadrant 3, that means both y and both x are going to be negative. So y will be negative 1, and x will be negative root 3. So that's my 1, 2, 3 triangle. That's a 30-degree reference angle. And x is the long side. X is root 3. So x is the long side of a 30-degree reference angle triangle. X is negative root 3, y is negative 1, and my radius is 2. So if I want to find cosecant x, that's the reciprocal of sine x, which is r over y. So my r value is 2, y is negative 1, so cosecant x would be negative 2. Now this time I'm looking for all the values within one period. Find each value of theta if sine theta is 1/2. So again, I know that sine theta is y over r, so that means that y is 1, r is 2. I'm looking at a 1, 2, root 3 triangle, the reference angle of 30 or 60 degrees. So 1 is the short side of the triangle. So my y is the short side. So looking for a 30-degree angle where y is shorter than x. I can draw that in two places. 1, 2, root 3, 1, 2, root 3. So now I just need to find the angles. Each 30-degree angle is pi over 6, so I have 1 pi over 6, 4, 2, 3, 4, 5 pi over 6. When is secant equal to negative root 2? I write this as a fraction, and I know that secant is the reciprocal of cosine, so this is r over x. Now my r can never be negative, so r must be root 2, which means that x has to be negative 1. So this is a 1, 1, root 2 triangle, which has a 45-degree reference angle, or pi over 4, where x is negative. So I'm in the negative part of the x-axis in quadrants 2 or 3. My radius is root 2, and my x is negative 1. So this is 1, 2, 3 pi over 4s. Each 45 degrees is pi over 4. And then 1, 2, 3, 4, 5 pi over 4. There's my two answers from 0 to 2 pi. Well, finally, what if tan squared is equal to 3? When you see this squared here, what it really means is that the whole function is squared. So that's tan theta squared. So if I want to solve for tan theta, then I just need to take the square root on both sides. Don't forget that every time you take a square root, you need to include the positive and negative sign. So tan theta could be positive root 3 over 1, or tan theta could be negative root 3 over 1. Now tan is equal to y over x. So this situation leaves two possibilities. Either x and y are both positive, or x and y are both negative. And this situation also leaves two possibilities. Either x is positive and y is negative, or x is negative and y is positive. So there's four different answers. This is a 1, 2, 3 triangle, 1, 2, root 3 with a reference angle of pi over 6, where y is the long side of the triangle because y is root 3. So y is long, x is short. So I've got two possibilities when tangent is positive, which are on a straight line there. And there's two possibilities where tangent is negative. All students take calculus. Okay, so we've got four different reference triangles. And we're talking about multiples of 30 degrees. So there's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5, 6, 7, 8 pi over 6, 9, 10 pi over 6. I can simplify all these fractions and write them over 3. Really, the reference angle is 60 degrees here. And I get four different answers from 0 to 2 pi. And you can verify all these answers by graphing both sides of the equation, graphing y equals tan squared x and y equals 3. So now what if there is a multiple angle? So cosine 4x equals negative root 2 over 2. And we can do this without the calculator. Okay. Remember from the transformations unit that cosine 4x really means that the cosine function has been taken and compressed 4 times horizontally. So what that means is that instead of being able to fit just one period of cosine from 0 to 2 pi, so So the normal cosine starts at the top, goes down, comes back up to 1 again after 2 pi. So now if I take that and I compress it 4 times smaller, now I can fit 4 of those ways. 1, 2, 3, 4, from 0 to 2 pi. And that goes from -1 up to 1. So I'm graphing cosine 4x from -2 pi to 2 pi, and maybe about -2 to 2 here. So now if I want to know, when is that equal to -√2 over 2? -√2 over 2 is somewhere around here. Okay. Normally, if I have a normal cosine graph, so normally for cosine, the graph has only 2 answers. So my basic cosine graph will cross at 2 points. But as you can see from the graph before, when we have a 4-time compression, one, 2, 3, 4. Now it's going to cross 4 times as many times. So instead of just having the 2 crossings, now we have 8 crossings fit from -2 pi to 2 pi. So let's see if we can calculate those answers. When you have a multiple angle problem, one thing that you can do is a substitution. So we can let 4x equal a. Then cosine a is -√2 over 2. If I unrationalize that fraction, it's the same as -1 over √2, which means that my x value is -1 and r is √2. So this is a 1, 1, √2 triangle, which has a reference angle of 45 degrees. So x is negative. I'm on the negative part of the x-axis at a 45-degree angle. There's 2 possible triangles where both the sides are the same. Okay, so each of these triangles has a 45-degree reference angle. So how many 45 degrees do I have? 1, 2, 3 pi over 4. 4, 5 pi over 4. Okay, so basically what I did was I solved on the normal cosine graph. Cosine A equals -√2 over 2. And now what I'm going to do is I'm going to take those answers and I'm going to compress them 4 times. So you can imagine I'm taking my hand and I'm just pushing on this graph until it becomes 4 times closer to the y-axis, 4 times smaller. And what that does is it makes all the answers 4 times smaller. So instead of being 3 pi over 4, this is now 3 pi over 16, 4 times smaller than before. To do that algebraically, we're just going to put 4x back instead of a, because a is the same as 4x. Let's put 4x back and then solve for x. So 4x could be 3 pi over 4, 4x could be 5 pi over 4. Now we'll divide both sides. Oh no. Okay, it kind of fixed. So now we'll divide both sides of the equation by 4. And when you divide both sides by 4, that's the same as multiplying by 1 over 4. So multiply the tops. 1 times 3 pi is 3 pi. 4 times 4 is 16. And that gives us our first answer there. Now we can do the same thing for the second point. Let's say that 4x is equal to 5 pi over 4. Divide both sides by 4. And you get x is equal to 5 pi over 4 times 1 over 4. or 5 pi over 16. So that would be the second answer. Okay, compressed by a factor of 4. So now it's wanting us to find all the answers from 0 to 2 pi. So actually, it's wanting us to find all 8 crossing points. Now there are 4 that are the same place on the wave as the red function, the red solution, which is 3 pi over 16. And all of those are just one period away from the original point. So first we need to figure out what is the period of this graph. Well, we know period is 2 pi over b. So p is 2 pi over b. B is this value here, 2 pi over 4. So b is the same as pi over 2. Now if I want to make that easy to add to my original answer, I just need to write it as the same common denominator. So my answers are going to be, my first answer is 3 pi over 16. My second answer I can get by just adding pi over 2 to the first answer. But 3 pi over 16 plus pi over 2 is kind of hard. I need a common denominator. So instead of pi over 2, I'm going to write this as something over 16. So to go from here, I need to multiply the top and the bottom by 8. So pi over 2 is the same as 8 pi over 16. So instead of adding pi over 2, I'm going to add 8 pi over 16. So when I add 8 pi over 16, that's the same as adding 8 pi to the top. So that becomes 11 pi over 16. So that'll be my second answer, 11 pi over 16. And then I add 8 to the top again, do the same thing, and I get 19 pi over 16. That gives me my third solution. And then add 8 to the top to get 27 pi over 16. I keep doing this until I get bigger than 2 pi. 2 is the same as 32 over 16. So as long as my numbers are on the numerator are less than 32 in this case, then I'll be within the domain. So now I'll do the same thing with my blue answers. The first one is 5 pi over 16. To find the second answer, I'm just going to add the period, which is 8 pi over 16. So I add 8 to the top, and that gets me the second answer. 8 plus 5 is 13. There's my 13 pi over 16 is my second answer. Third answer is adding 8 to the top again, 21 pi over 16. And my fourth answer comes from adding 8 again, 29 pi over 16. And I stop as soon as the numbers get bigger than 2 pi or less than 0 because of the domain. And there are my 8 solutions. So now we come to some fun questions, which are quadratics. To solve the equation cos x squared minus cos x minus 2 equals 0, we need to recognize that cos squared x is the same as cos x all squared. Whenever you see a cosine term that is squared, it's really helpful to do a substitution. Let cosine x equal some other letter, like a. Then we turn a grade 12 problem into a grade 10 problem. A squared minus a minus 2 is 0. And now we can factor. What two numbers multiply to a squared? We need a times a. What two numbers multiply to negative 2? Well, 2 times 1 is 2. And then when I add the middle terms and the outside terms, I need to get negative 1. So that means my 2 must be negative and my 1 must be positive. Okay, so a is negative 1 or a is 2. There's 2 solutions. So now now that I've solved the quadratic, I can put my cosine back in since a is actually cosine. So either cosine x is negative 1 or cosine x is 2. Let me just think about what this graph looks like. Cosine starts at the top, goes down, comes back up again, and it stays between 1 and negative 1. If I graph the line negative 1, that looks like this. It crosses at just one point, halfway between the beginning and the period of 2 pi, so it crosses at the point pi. Now when is cosine x equal to 2? Well, cosine x goes from negative 1 up to 1, and the line y equals 2 is above, up here somewhere. So these two lines will never cross. Okay, so there's one solution, which is x equals pi. Now to write the general solution, we want to write all the answers from 0 to infinity. These answers will repeat every period. So we add the period n times, where n is an integer. And there's the general solution. Okay, so we'll do one more factoring problem. We're given 2 sine squared x minus 5 sine x minus 3 equals 0. I want to find the solutions from 0 to 2 pi, and then the general solution. And naturally, you can also do this on the graphing calculator. But it's important to be able to show your steps. So the first thing that we do when we see a problem like this is let sine x equal some other variable like a. Then we're going to change this grade 12 problem into a grade 10 problem. Okay, so to factor this, I need two numbers that multiply to 2. Those will be to 2a squared. That'll go in the front. So there's only one way to get 2, and that's 2 times 1. Okay, my two last numbers have to multiply to 3. So that would be 3 times 1. I've got no other options. And then my inner and outer numbers have to add up to negative 5. So let's see. Here I've got 6. Here I have 1. So if my 6 was negative and my 1 is positive, then I would get negative 5. So there's my two factors. 2a plus 1, 1a minus 3. So this gives me two solutions. Either a is 3 or a is negative 1/2. So now that I've found my two solutions, I can put sine x back in. So either sine x is negative 1/2 or sine x is 3. So let's think about what the graph looks like. Sine x is negative 0.5. That'll cross in two places. Whereas sine x equals positive 3, since sine has a maximum of 1, this will never cross. So now I can think of it in terms of x, y, and r again. So sine is y over r. So that means that my y value is negative 1 and r is 2. That's a 1, 2, 3 triangle on the unit circle. Let me draw a unit circle over here. So my y is negative, my y is short. That's going to be here and here. So I have 1, 2, 3, 4, 5, 6, 7 pi over 6. My first answer is 7 pi over 6. And my third answer, 7, 8, 9, 10, 11. My second answer is 11 pi over 6. Okay, so there's two solutions from 0 to 2 pi. And for my general solution, I take those two answers and add the period. Because this sine curve is going to repeat again, and I'm going to get two more answers just one period away. So when I add 2 pi, that gives me another answer. And same thing for the 11 pi over 6. If I add the period once, then I'll get another answer. And n can be either positive or negative, any integer. So just some last thoughts. How does a solution obtained graphically differ from an exact solution? The graphical answer is only approximate. Your calculator can only hold so many decimal places of accuracy, of precision. Does a solution obtained graphically ever equal the exact solution? Yes. If the solution is a whole number or an integer or some simple fractions like 2.5, but if the answer is pi, then it could never really show all the decimals in the solution. So your homework for this set is from page 480, numbers 1 to 4. Sorry, page